So uh, today's presentation is about mechatronics, a future trend of engineering. And I want to start with the map of mechatronics. So this is broadly showing us how and what mechatronic major is. And then from there, I will actually show you some examples of the kind of work that I'm doing in mechatronics and how I'm using these skills and uh, these skills to develop mechatronic systems. So I will start with the first actual story is with the gravity and with the law of gravity. So it started more than 200 years ago in 18th century by Newton. And he was the one who was formalizing the all mechanical stuff. So he developed, based on calculus, laws of motions. So based on this, we had a better understanding of how physical works in the mechanical domain was actually developed. And then based on these foundations, people continued, and then there were more contributions. So we had the fluid mechanics and we had classical mechanics. So these are the parts of actually things that was covered traditionally in mechanical engineering and in those sort of majors. And then sometimes later in 19th century, we had Maxwell. And Maxwell was the one who was formalizing and who developed the formula for electromagnetism. And that was basically foundation for electrical engineering. So he was the one who was actually doing the contribution for developing the electrical engineering and then those sorts of things. And then in 20th century, we had Turing, and then Alan Turing who was considered as the father of computer science. So he developed the computer, and he developed the first idea of how we can do the computation and how we can have those sort of machines. We can do the computation for us. And this changed everything, because then there were contribution and interaction between electrical engineering, mechanical engineering, and computer science. So every computer that we are using now was basically developed based on the concept of Alan Turing. And then we had actually more precise computation. We worked on scheduling and processing, and we increased the processing power. And now we have microcontroller, microprocessor to be used. And this is the combination of computer science and electrical engineering. And then we were using computers to do the optimization, because that's very important. So every design that we have in classical engineering needed to be optimized. And then with the help of the computer, we were able to do this sort of optimization. And then computer science further developed based on those optimization skills. We developed artificial intelligence. Now we had the computers which are able to think to some extent and do some intelligence stuff. And then the branch that was doing lots of help to this is machine learning. And these are the kind of things mostly on the computer side. And there is huge interaction again with the computer and mechanical engineering. So now we have the computer-aided design, computer-aided manufacturing, we have 3D printing, and then we also have the sensor and actuators, which are combination of these things in order to have interaction with the physical domain and actually sensing the physical domain. So this is the whole map, but the core of this is this part. So the core skills needed for developing mechatronic systems are being able to manufacture them using 3D printing and computer-aided design, being able to interact with the physical domain, getting data and doing some physical things, so that's sensor and actuator, and being able to process those interactions using microprocessors and using microcontrollers, and then designing and understanding all of this through machine learning and AI. And these are the sort of modules that we develop directly and indirectly in mechatronics, and we are actually working on them in University of Essex. So what can you do with that? there is a quote from Picasso that I really like. He says that everything that you can imagine is real. So what I was imagining, and then these are the robots that I built. So I'm doing small scale robotic and mechatronic. So I actually make very, very small robots to do medical stuff. So to do drug delivery and very small surgeries or interactions. So these are some examples of that. And then I want to bring these skills to developing these sorts of things. So I want now to show you how I'm using these different skills to develop these mechatronic systems. So I will give you one example to show you how it works. So back in 1966, there was a book called Fantastic Voyage. And the Fantastic Voyage, and this is an imagination, yes? So Fantastic Voyage was about a miniaturized submarine which was going to open a blood clot in the brain. So they made a miniaturized submarine. They injected it into the veins, and then they actually moved it to the brain to open a blood clot. And they made a movie out of it. So here is the injection. So there is a very small submarine inside the syringe. And then they are trying to put that submarine into the vein like this, and then monitoring its movement to reach to the brain and open a blood clot in the brain. And they had these radars all over the patient to monitor and to find the path. So this was the idea, this was the imagination. So what we do in mechatronics is that we take that idea and make it real. So how can we make it real? So initially, what are the parts involved? So the application was opening a blood clot, and for that application, they were using lasers. And the robot that they used was a submarine, a miniaturized macro scale submarine. And then they were actually using that to go to the location of interest, which was brain in this case. And the powering was done by nuclear energy. So they were actually powering the submarine with nuclear energy. And then they were using these external radars to monitor the submarine. So it was a very nice idea. It was a very beautiful idea. So how could we do it reality? So in reality, things are a little bit different. So when we go back, obviously we cannot still, I don't know about the future, but we cannot still miniaturize a submarine. So instead of miniaturizing submarine, we can now miniaturize devices. This is my macro robot, which is a tethered macro robot, and which is actually a 500 micrometer. It's smaller than hair. And obviously, we couldn't use nuclear energy for this, but we had a better source of energy called magnetic energy. This is very safe, and we could use magnetic energy to actually guide these robots. So I started using magnetic powering for these macro robots. And then the idea of the radars was nice at the time, but now we have quite fascinating equipment like X-ray, MRI, and then we can use them to monitorize and to see the objects in real time. So this is the X-ray image of the macro robot in reality, and then we could actually do the tracking of that. And we could do the same thing. So now I want to show that how we bring that mechatronic designs into reality. So this is a video. This is an image of the computational model. So we generally, as I mentioned, there are lots of different subjects involved in mechatronics. So generally, we develop a model similar to this, and then we use this model in order to design stuff and in order to make it real. So this is the first step. And the second step is fabrication. So we fabricate that, and then we actually show that it is matching to the reality. It is doing what we wanted to do in initial step. And then we will do it in more practical, more realistic ways. So here, the goal is to use this complex structure and go from one point to another point using this external magnetic field and then moving the macro robot inside this complex environment to reach some goals. And here the goal was opening a blood clot. So this is the 2D model, and finally we did it in 3D. So this is real blood clot, a real blood vessel. So this is in actually very small scale. The diameter is 2 millimeter for these blood vessels, and then the macro robot is moving inside these blood vessels to go to some desired direction and then do something for us. So this is basically the core knowledge of sensor and actuator fabrication and then monitoring in order to develop a real mechatronic design. So yeah, this is my, I did the first presentation, and thank you for listening to this. Dr. Lee will continue with his presentation as a second part. So the second 10 minutes would be with Dr. Lee. Thank you.
Good afternoon, everybody, and welcome to SX. So following Dr. Ali presentation, so I will do a presentation about same scheme and about some of my project. My name is Jichun Lee, and I'm currently a lecturer at CSEE at SX. So first of all, I will introduce what is mechatronics, and then I will explain a mechatronic engineer's job by a project I delivered before for Nissan plant at Sunderland. So mechatronics, so it's a broad combination of mechanical engineering, so electrical and electronics engineering, controls, software programming, and information technology. Mechatronics engineering, so focus on the research, design, manufacturing, and the test of more efficient and intelligent automated equipment with the potential to help people. So we can find mechatronics anywhere in the world. So industrial robotics, so CNC machines, so laptops, so cameras, so cars, 5-speed trains, so drones, so military application, medical application, anywhere. So mechatronics, that's the future of the engineering. So what does a mechatronic engineer actually do? So here I give you an example. So it's a real project. So you see here is a electric car, so Nissan Leaf. So, you know, people are concerned about the battery of the electrical vehicles. So they are concerned about the battery life, so battery failure or something like this. So as the manufacturer, so Nissan, they would like to get, each battery cell or battery module or battery pack to be checked at the plant. So they want to know the battery is good or battery is bad. So they want to do a very quick or fast check. So that's the requirement from this project. So here you can see that's the production line in a Nissan battery plant, manufacturing the battery cells. So the idea is they would like to get a mechatronic system to pick up the battery cells from the production line and then do a quick check and then return these battery cells to the battery line, production lines. So that's the environment. So as a mechatronics engineer, you are going to do the following jobs. You need to do, first thing is you need to understand the requirements from the customer and do some specifications to how to design these mechatronic systems. The sixth step, so you, as a mechatronic engineer, you have to do project management. So this job including this work plan or cost plan, so budget, so purchasing, so workload allocation, so team building, so things like this. So that's the project management. That's part of the mechatronics engineer's job. Then after you define this specification, and now you start to design. So basically, so mechatronic system, including the mechanical design. So usually you will use the CAD software, such as SolidWorks or Creo or other computer-aided design software to build this model for this mechanical part. So at the same time, you should design this hardware. So this hardware maybe it has a core of the microcontroller, or you can use your PLC or use the industrial PC. So sensors, actuators, so integration about this hardware. So that's the second step for this hardware design of the mechatronic systems. So the second step could be the software design. So you need to design the human machine interface for the user, to how to operate this machine. So behind this UI, it is the software design. So it's the flowchart, so coding, programming, so debugging, something like this. So that's the mechatronics software design. So based on this integration of the mechanical design, so hardware design and software design, usually you build up this machine. So after build up, there's need in factory test, and then delivery, and then outside test. So here you look at that's the real machine, so placed alongside the production line of Nissan plant. I have a short video. It shows how this project works. So you can see there's a box with the battery cells are loaded via the production line. So this machine will automatically stop this magazine. Then you can see the gripper will move forward and catch up the electronic parts for this battery cell, then do a quick check. So that's a novel sensing technology, so that we call it EIS. So that's the measurement procedure. And we can see here is the touch screen. So it's controlled by the PLC, and on this test form, there is a software, human machine interface. So control the data acquisition from this sensing unit. So you can see the data we acquired from these battery cells. And also you can see there will be a graphic display on the right side of this screen. So that means we using this software to acquire data, analyze data, and showing the data and storage the data for future applications. So big data, something AI application, something like this. So this system could be remotely controlled by the central control unit at the Nissan plant. It also has the local display and monitoring system. It can be run via this laptop or other industrial PC. So this is just for test purpose. You can see different curves. It shows the battery has different quality. So we can identify which battery cell is good or which battery is bad. So here I got a few reading lists. So you can see about what is mechatronics, so how this mechatronics is run, some projects from my research. So thank you very much for listening. Any question?